Okay, welcome back to our discussion of Chapter 14, Sorting and Searching. Previously, we had a chance to look at insertion sort and selection sort. These two sorting mechanisms worked in order n squared time, meaning as the input of the array that you wanted to sort grows larger, the amount of time grows as time squared. So you double the size of your array that you want to sort, the time goes up by 4. You multiply the time, if the size of your array goes up by 10, then the time is going to go up by 100. Your length, the ratio of time goes up as the square of the ratio of the size of your input. So that's not great because we often need to work with large amounts of data when we're using computational approaches to problems, including databases and all of those similar kinds of repositories of large data. And fortunately, we know about a slightly better, not a slightly better, a dramatically better family of algorithms that use an approach called divide and conquer. Divide and conquer seems like a pretty simple idea, but in fact, it's dramatically different in terms of the running time for sorting. And one of those algorithms that does divide and conquer is merge sort. I'd like to look at this one and try and understand a little bit about how it differs from insertion sort and selection sort. Now, the idea behind merge sort is that it's going to work by cutting an array in half and then using the technique that we've already looked at, which is recursion, and then treating each half of the array as its own little array to be sorted and recursively trying to sort each of those smaller arrays that have been split in half. When each of those smaller arrays comes back, they're individually sorted, but they're not sorted across the whole range of data that you've put in. And so you get two sorted arrays back and you need to merge them together. Part of the reason why this is so fast is because that merging process can be done very fast as well. Overall, it's a much faster algorithm than selection sort and insertion sort. So let's take a look at how this operates with an example. Let's imagine that we have an array like the one at the top, and we're going to divide it in half. So we have a left half and a right half. And we're going to assume, because we're using recursion, that each side has been sorted. And so you see that what comes back is 5, 9, 10, 12, 17. The lower half of the array has been sorted. And the upper half of the array, 1, 8, 11, 20, 32, has also been sorted. So because we have this property of recursion, understanding that if we can split the problem into something smaller, and we have a base case, basically when your half of an array has one or just two elements in it, then you can do an inductive step or recursive step and assume that it worked, and then say, well, what do I do now that I have gotten back two sorted arrays from my recursive call? Well, now you merge it. And the thing that makes merging very fast is you only have to, at any given time when you're merging, look at the lowest two elements of the two halves of your sorted array. So as you go through the two halves, you keep what we call a pointer or some kind of index at the lowest element that you've evaluated on each array. So you start out by looking at 5 and 1. Because those are the lowest elements in each of the subarrays, you know that there's no other lower element anywhere else. And so you only have to decide between 5 and 1 which one is lower. You decide that 1 is lower, and so you move it over into your finished array. That's that first row. And then you advance the pointer on the right sorted list so that it's now pointing at 8. And now you consider 5 and 8. 5 and 8 are the lowest two elements that remain in each of the smaller arrays, so you know that it's going to be one of those elements is the next smallest element. You say 5, okay, 5 is less than 8, so we add that to the sorted array. Now our pointer on the left is pointing at 9, and the pointer at the right is pointing at 8. We have to choose between 8 and 9. 8 is the lower element, so we move that over. Now our pointers are pointing at 9 and 11. Between 9 and 11, we choose 9, and so we move that over. And now our pointers are pointing at 10 and 11. Between 10 and 11, we choose 10. Now our pointers are 12 and 11. Between 12 and 11, we choose 11. Now our pointers are 12 and 20. Between 12 and 20, we pick 12. Now our pointers are 17 and 20. Between 17 and 20, we pick 17. And now we're out of data on the left-hand side, but we still have two data elements on our right-hand side. No problem, because we know that our right-hand side is sorted. So if we run out of elements on one side of our array, we just copy the remainder elements that are already sorted from the subarray into the final array. So we copy over the 20, we copy over the 32. And in this way, we've completed the sorting of our array by doing merge sort. Conceptually, this is what's happening. Let's take a look at what that looks like when you put it into code. Here's a little snippet. It's not complete code, but it shows you what a sort might look like doing merge sort, where what we take in is going to be an array, a reference to an array that we're giving the name A and our parameter. And what we're going to do is we're going to sort that array in place. So the first thing that we'll do is we'll check for our base case. If the length of A is less than or equal to 1, meaning we have 1 element or 0 elements in it, we just return, because an array with nothing in it or an array with 1 element in it is already sorted. So that's our base case. It's the smallest case that we're handling recursively, so that's an important thing to have nailed down if you're going to do a recursive solution. Then what we need to do is we need to create some space in order to hold our two subarrays. So we'll call the first one first and the second one second. We'll allocate 2 arrays of ints, and you can see here that what we're doing is we're going to first divide the length of A in half by 2. Now notice we're doing integer division here, meaning we're going to throw away the fractional component after we divide the length of A by 2. An integer divided by an integer gives you an integer. Now, maybe when we were going over these operations, it seemed silly to ever want to throw away the fractional component in a division operation, but here we see an example of why it's important to have an operator like integer division. Because we want to split an array in half-ish, but we don't want to have half an element in our subarrays. We either want it to be one smaller or one greater, but we want it to be integral. So our first array is going to be a.length divided by 2, and the second one is going to be whatever's left over, a.length minus first.length. Now what's not shown here is the process of copying over the data from A into first and second. I don't show you that because that's a simple application of loops, and hopefully by now that seems like it would be straightforward. Once we copy the data over into first and second, then we recursively call on our 2 subarrays. We call sort first and we call sort second. What comes back is first and second has been sorted, and then we merge first and second and put it back into A. And then when we return from merge sort, A has been sorted in place. So what I'd like to do is I'd like to give you some time to look at the code for merge sort here, and then we'll move on to our next topic. All right, thank you for your attention.